Hello, my name is Lena, I'm a PhD in mathematics, and here I try to demonstrate how often we use mathematics in our life, even if we don't think at the moment about mathematics. Today I want to speak about our future, but not very distant. Quantum computers. It seems like some fantastic device, as a magic carpet, but it's not true. Now there are commercial devices working in quantum principles, and the price is about $500. How it works, and how perspectives quantum computers are. We will talk about this. Let's go.
Liftoff of the Delta rocket carrying GLAST.
What is a quantum computer? This is a device consisting of qubits, quantum particles. They are in the quantum superposition. What does it mean? There are two boundary states, and our particle is in the both states at the each moment, until we measure the state of the particle. For help to represent it, Schrödinger used a Schrödinger's cat. This is a cat closed in the metal box, and we push a relay that passes an electric current through the metal box, or not passes, with 50% probability. And for us, until we open the box, the cat is dead and alive with 50% probability. As for me, I think Schrödinger is slaughtered, and we will have our Schrödinger's cat that's always alive. This is Charlie. Charlie almost always is in the quantum superposition. He is full and hungry at the same time, and we can't see if Charlie is full or hungry. We can only suggest Charlie to eat, and if he eats, then he has been hungry, and our measuring changes the system. We can imagine the qubit as a vector on the sphere. If the qubit is in a quantum superposition, then the vector is directed in all directions at the same time. If the probabilities with which the qubit would take the values 1 and 0 were the same and evenly distributed, this picture would be enough for us. But these probabilities may be different for each qubit position. We can imagine the probability that qubit will take the value as 0 as a layer of probabilistic oil unevenly smeared onto this ball. At each point, we can determine the thickness of this layer by a vector. It will have a length and direction. We can do the same for the probability that the qubit will take the value 1. The sum of the lengths of the vectors for probability 0 and probability 1 at each point will give 1, because the probability that the qubit will take at least one of the values is 1 or 0 equals, obviously, 100%. These vectors are called probability amplitudes. Quantum particles have an amazing property named quantum entanglement. We can entangle two quantum particles far apart from each other. For example, one in London and another in New York. And it is absolutely incredible that if we measure one of the particles, then another absolutely simultaneously be also in some state. For the investigation of quantum entanglement, the Nobel Prize in Physics was awarded this year. Charlie and Gosha are quantum entangled. If Gosha eats, Charlie eats too, because he is afraid that Gosha will eat everything and Charlie will rest hungry. And what can it give us? Now let's figure it out. Imagine that we want to sit in two taxis full of people, and some of these people are at enmity with each other. We need to sit them so that the enemies don't have to ride together. This task can be resolved by simple numeration. There are to the fourth power variants, and it is an easy task. We can resolve it even with a calculator. And what if we need to sit 100 people in two buses. If we can resolve this problem only by enumeration method, and we can't optimize our enumeration, then we need to make so much operations. For make it with supercomputer, we need so much time. It is more than the lifetime of university. In this case, we use a classic logic. In the origin, here are the bits. They can be in two states, 0 and 1. In our task with 100 people, we have 100 bits, and each takes a value 0 if these people sits in the first bus, and 1 if in the second. And what if there exists another way to calculate all the possible numerations? And another way really exists. If you take 100 qubits that are in both states simultaneously, each people is in the first bus and in the same time in the second, and qubits are entangled, this allows to take into account that some people are at enmity with each other, that only 50 people can be placed in a 50-seater bus. Using the simple algorithm, we can solve this problem in about a quadrillion operations. It is the root of that huge number. It is also a very big number, but a supercomputer can resolve it for a second. And what is the magic algorithm? It is possible due to the quantum properties of qubits and due to our possibility to change a quantum entanglement between qubits. Let our problem of finding the optimal solution have exactly one solution. Our quantum system contains information about what kind of solution it is. It looks like this. It is known from geometry that if all sides of two triangles are equal, then the triangles themselves are equal. However, this is not obvious. But if you take two sets of identical segments and try to assemble two different triangles from them, they will still turn out the same. The conditions of our problem, data of all sides of the triangle, contain information about the angles in a way that is not obvious to us. Something similar happens with the quantum system. It contains information about the solution and we just need to get it. So we have 2 to the power of 100 qubits states. It seems like finding a needle in a haystack with a magnet, and it is named Grover's algorithm. We can imagine the state what we search as a magnetized needle, and it remains for us to find it. Do you remember the probabilistic oil, the probability amplitudes of qubits? When we have a system of 100 qubits, we can see this in another way. So we have 2 to the power of 100 states. One of them is the same magnetized needle. Each state has its own probability amplitude. We can imagine it is a strip with columns. Each state corresponds to a strip looking up or down, having some height. One of the states is a magnetized needle. Note that we can draw a line. This is the average of all probability amplitudes. We have a device, a magnet, which has 2 poles. Firstly, we use the same pole which is a needle's pole. Then we force the needle to turn around. Its probability amplitude changed sign, and the average of probability amplitudes will move in the same direction where the amplitude turned over. The second magnet's pole turns all the amplitudes about the average, and the amplitude that was at the bottom become very big, and at the top, our needle came out of the haystack. Since this all has probabilistic origin, in order to get the value with the maximum probability, we will have to perform this operation about the root of 2 to the power of 100 times. And how does it work in life? Physical system, realizing qubits, can be any objects that have 2 quantum states. Polarization states of photons, electronic states of isolated atoms of ions, spin states of atomic nucleus, and so on. Now, the development of quantum computers can be divided into two big areas. Firstly, specialized quantum computers that are aimed at solving one specific problem. For example, an optimization problem. An example of these quantum computers is D-wave quantum computers, and there are already 5,000 of qubits. It is fantastic. Secondly, universal quantum computers. They are capable to implementing arbitrary quantum algorithms. There are implementations, for example, from IBM and Google. The largest value declared to date is the Chinese prototype of a quantum computer with 66 qubits.
Scientists have established a quantum computer prototype named Zhuzhong 2.0 with 113 detected photons, achieving major breakthroughs in quantum computational speedup.
And there is the smartphone that you can buy not for $1 million. Its price is about $500, and it has a quantum random generator. It is cool because always when we generate a random number, it is not random for real. This number is generated by complex calculations, and this is bad for security. And here is a cloud service that allows to program on multiple qubits right now. And what does all this give us? If you watch films where a person walks through the forest, for example, it is very believable. But for a second we see that is not true, and all this image is generated by a small box. Now we can't render sense of this magnitude, but a quantum computer can. Or do you remember in the film Back to the Future, the professor, looking at this watch, said that it would rain in 2 minutes. Modern computers cannot calculate the recurrent set of information to accurately predict the weather, but a quantum computer can. Or do you remember how long it took to develop a vaccine against coronavirus, despite the fact that its prototype has been known de facto for 10 years? And a quantum computer would simulate this in a maximum of hours. Economists say that the financial crises are unpredictable. And if you take into account absolutely all the parameters that a quantum computer is capable of, then there will be no financial crisis. Well, and so on, and so on, and so on. This is a real breakthrough.